The sun was not always the center. For over 1,300 years, Earth ruled the cosmos on paper. That sounds like a mistake waiting to be corrected. But the strange part is that the old model worked. It worked well enough to survive. Around 150 CE in Alexandria, Claudius Ptolemy formalized a geocentric system in the Almagest, using deferents and epicycles to model planetary motion. Circles inside circles helped explain one of the sky's most famous puzzles. Planets sometimes appear to drift backward against the stars. But here is the contradiction. The idea that Earth moves around the Sun had already been proposed by Aristarchus of Samos in the 3rd century BCE, long before Copernicus. So why didn't the sun-centered idea win then? And why didn't Copernicus win instantly when his book appeared in 1543? This is No Science. The real story is not one genius moving everyone at once. It is the story of how a universe can be mathematically useful, philosophically persuasive, and still eventually give way. Geocentrism was the dominant pre-modern framework for understanding the heavens. Not just a comforting picture with Earth in the middle. In most versions of the model, Earth sat near the center, while the sun, moon, planets, and stars moved around it. To an ancient observer, that looked reasonable. The ground does not seem to rush beneath our feet. The stars rise, cross the sky, and set, while Earth feels solid. Aristotle helped give that picture physical and philosophical weight, but Ptolemy gave it a machine. In the Almagest, the heavens became geometry. A planet could move on a small circle, the epicycle, while that small circle moved around a larger circle, the deferent. This was not random patchwork. It was a mathematical strategy for turning messy sky paths into predictable patterns. That matters because ancient and medieval astronomy was not only about wonder. It supported calendars, timekeeping, astrology, religious observance, and the authority of inherited learning. Across European and Islamic mathematical astronomy, Ptolemaic methods were copied, criticized, refined, and taught for more than 1,300 years. If a model let you calculate where a planet would appear, it had power. So the first partial answer is this. Geocentrism lasted because it was not intellectually lazy. It was a serious mathematical framework built from the observations and assumptions available at the time. But the machine had a cost. The more carefully astronomers tracked the planets, the more geometry the machine seemed to need. And that is where Aristarchus becomes more than a footnote. Move now from Alexandria back to Samos, centuries earlier, where a simpler question could be asked. What if Earth was not the still stage beneath the heavens? What if Earth itself was one of the moving bodies? Aristarchus of Samos proposed an early heliocentric idea in the 3rd century BCE. That does not mean he produced the later Copernican system, and it does not mean he settled the structure of the cosmos. What he showed was that the old question could be inverted. Instead of asking how the heavens moved around Earth, you could ask what the sky would look like if Earth moved. That is a profound change in viewpoint. But a viewpoint is not enough. A working astronomy has to calculate where planets appear, night after night, year after year. It also has to survive the habits of its own culture. A moving Earth raised hard questions. Why do people not feel the motion? Why do falling objects behave as they do? And why do the stars not obviously shift across the year? Those were not foolish objections. They were the exact pressure points any serious moving Earth model had to answer. That is where the old Earth-centered machine still had the advantage. The geocentric model could absorb irregular appearances through epicycles and refinements. The heliocentric idea had elegance, but elegance alone does not make an astronomical instrument. This is the key distinction the myth usually skips. Aristarchus did not make later astronomy unnecessary. He exposed a possibility that would wait for a stronger mathematical engine. And that engine had to solve the strangest visible clue in the sky: retrograde motion. Picture Mars over many nights, not as a red dot in one photograph, but as a trail of positions against the stars. Most of the time, it drifts one way. Then it slows. Then it appears to move backward. The planet is not literally reversing direction in its orbit. Retrograde motion is an apparent change caused by changing positions and sightlines, especially when Earth overtakes an outer planet. But if you begin with Earth fixed, that loop is hard to explain simply. Ptolemy's answer was not to laugh at the loop. It was to build geometry that reproduced it. A planet on an epicycle could sometimes move in a way that made it appear to backtrack from Earth. That is why the Ptolemaic model was so durable. It took the visual weirdness of the sky and made it calculable. Now switch viewpoints. If Earth is also moving around the Sun, retrograde motion becomes easier to picture. When Earth catches up to Mars and passes it, Mars seems to slide backward against the more distant stars. It is like passing a slower car on a road. The car beside you appears to fall backward, even though it is still moving forward. That explanation is powerful because it turns a loop into a consequence of perspective. It also gives the moving Earth a visible job. Earth is no longer just the place where observation happens. Earth becomes part of the mechanism that creates the observation. That is the operational reveal. The same Mars loop can be treated either as a motion to be manufactured by circles or as a clue that the observer is moving too. But the sky did not hand astronomers a simple scoreboard. A model could explain the broad pattern and still miss exact positions by enough to matter for serious calculation. Those offsets mattered because astronomy was operational, not ornamental. A small error in a planet's predicted place could ripple into tables, teaching, calendars, and arguments about which mathematical scheme deserved trust. So the debate was not just about which picture felt cleaner. It was about whether the new arrangement could earn the same practical authority as the old machine. But here comes the wait what moment. Even Copernicus still used circular motion and epicycles. The model that moved Earth from the center still relied on the same circles it was replacing. That does not make Copernicus unimportant. It makes the transition more interesting. Copernicus changed the architecture of the cosmos, but he did not yet have the missing shape that would make the predictions sharper. So the real question becomes sharper. If the sun-centered model was not instantly more accurate, why did it matter so much? The scene shifts to Nuremberg in 1543, where a book enters the world through ink, paper, and metal type. Copernicus's De Revolutionibus Orbium Celestium made Earth a rotating and orbiting planet. That was not a small edit to an old map. It changed what Earth was. Earth became a planet, not the unmoving reference point from which all other motion had to be explained. That reclassification was the deep shock. But the book did not instantly make geocentrism obsolete. Late Ptolemaic models were still mathematically sophisticated. Copernicus's system kept circles because circular heavenly motion still felt mathematically and philosophically natural in that tradition. So its predictive edge was limited. The early heliocentric model was not modern astronomy with the old labels removed. It was a bold restructuring that still carried old mathematical commitments. That is why acceptance unfolded unevenly across regions, institutions, and communities. Some readers saw a better cosmic arrangement. Others saw a useful calculating device, a dangerous philosophical claim, or a model that still needed more proof. Galileo would later add telescopic evidence, but even that was part of a broader chain, not a lone finishing blow. The turning point had to pass through instruments, tables, printing, argument, and repeated comparison with the sky. And then, the sky itself became harder to ignore. At Uraniborg in the late 1500s, Tycho Brahe made high-precision naked-eye observations before the telescope transformed astronomy. Those observations mattered because better data makes old compromises more visible. If your measurements are loose, several models can look good enough. If your measurements tighten, the wrong curve starts to show. This is where Johannes Kepler changes the story. In 1609, Kepler published his first 2 laws of planetary motion in Astronomia Nova. The crucial move was not simply putting the sun near the center. It was allowing planetary paths to be ellipses rather than perfect circles. That missing shape gave heliocentric astronomy a stronger predictive foundation. It also changed the meaning of simplicity. The simpler model was not the one with the prettiest circle. It was the one whose geometry made the measurements fall into place with fewer strained adjustments. Now, the earlier pieces clicked together. Aristarchus had opened the possibility that Earth could move. Ptolemy had shown how powerful a mathematical astronomy could be. Copernicus had rebuilt the cosmic architecture around a moving Earth. Tycho made the data harder to evade. Kepler supplied the new geometry and motion rules that circular models could not. The shift was not a single hammer blow. It was a chain of questions that made the old center harder to defend. So what did Aristarchus of Samos actually establish? Not the full modern solar system. Not a finished theory that could defeat Ptolemy's tables on its own. What he established was more basic, and in some ways more dangerous. Earth's central position was a question, not a necessity. Once that question existed, later astronomers could return to it with better mathematics, better instruments, and better data. The sun-centered cosmos did not gain force because it was simpler in every early calculation. It gained force because it changed the question from how everything moves around us to where we are moving from. That is why the opening map matters. It is not just an old picture of a wrong center. It is a record of how long a useful model can hold authority before better evidence changes the role of the observer. That is the memorable compression. The revolution began when Earth stopped being the stage and became one of the actors. This old sky map reminds us that evidence does not just add facts. It can move the place we think we occupy. But astronomy is not the only science where a better viewpoint changes the whole picture. I'm here to help you know how old questions become modern experiments. Which model would you test first? The geocentric model or the heliocentric model? Tell me in the comments. Thanks for watching.